My name is Nina Cardinal. I'm the National Technical Manager of Hansen Cement, and I want to speak to you today about new cements for sustainable concretes. Before going on to that, I just shortly want to introduce our company for those who don't know us. Hansen Cement are UK-based and operate in the UK. On the left-hand side here of the slide, you can see some statistics about our company. But to keep it short, we are a national supplier of cement, ready-mix concrete, aggregate and asphalt. We supply quality assured concrete from 178 plants across the UK. And with regards to cement making, we have 3 plants, one at Ribblesdale, one in Padeswood and one in Ketton. And we have also 3 plants which make ground granulated blast furnace slag, GGBS, which I will come back to throughout my talk as well. One in the north in Teesside, in Purfleet in the south, and in Port Talbot in Wales. My presentation for today is divided into 4 parts. I will first give you a little bit of background to our challenge, CO2 challenge for the cement and concrete as cement and concrete manufacturers and our responses to this as an industry. I will then introduce the new cements, first explaining how cements actually work before moving on to the new cements and how they link into the ready-mix concrete standard. I will then touch on some future developments before finishing the summary and then moving on to questions. So first of all, what is our challenge and the response to it? On this slide, on the y-axis, are the CO2 emissions per ton of cement produced. That is Portland cement, traditional Portland cement. As you can see, about 2/3 of the CO2 emissions are associated with the process itself. This comes from the calcination of limestone to lime. That by the laws of physics, we release CO2 in this process and cannot change it. This process involves a lot of heat, preheat, to pre-calcine the material, and then to heat the kiln to about 1400 degrees. And for this, we require fossil fuels. These again are associated with CO2 emissions. We also need a small amount of electricity to grind our raw mill and the clinker and to run the crusher. With regards to transport, virtually no CO2 emissions are associated with transport because we quarry our materials on the site where we also make the clinker and the cement. I am aware that there are other speakers today introducing the UK concrete and cement roadmap to beyond net zero. However, it is also quite key to my presentation, so I just want to shortly speak about it. This is where we are now around 2018 when it was derived. We have reduced our CO2 emissions by more than half since 1990. If we now look into the future, we want to come to that net zero, that dark line here. And a number of steps will be involved in this. Reducing the emissions associated with electricity, reducing emissions associated with transport, for example, by moving more from road to rail transport. Then what I will talk about later in this presentation, low carbon cements and concretes, new cements here, different fuels. And then you can see a large proportion of this plan depends heavily on this orange part here on carbon capture and usage and storage. Given that carbon capture is so important in part of this plan to achieve net zero, I just want to say a couple of words about this. The lovely photograph here at the top is a photo of the Heidelberg Cement Brevik plant, cement plant in Norway. We as Hansen are part of the Heidelberg Cement Group. At this plant, the first industrial scale development will take place of a carbon capture and storage plant. This has been approved and construction will actually start this year, and we aim to capture by 2025 to be operational by then and capture 4,000 tons of CO2 per annum. Similarly, the Heidelberg Cement Group, together with other cement manufacturers, are involved in a European-sponsored project, which again looks at a different technology for carbon capture. It's the LILAC project. In the first phase, a small demonstration plant was built in Belgium, and now this project has entered and received funding of 25 million for a second stage demonstration plant, which will have a capacity of 100,000 tons per annum. And this plant will be built again at the Heidelberg cement plant in Germany, in Hanover. And like the Brevik plant, it should be operational by 2025. Closer to home now in the UK, some of you will probably have heard that Hansen have recently joined a consortium, the HyNet consortium, which has a target of basically to reduce the regional CO2 emissions in the northwest of the UK by 10 million tons. As part of this initial funding, Hansen have been granted some funding to do a feasibility study of a potential carbon capture plant associated with our cement works in Padeswood, just into Wales. Again, you see them here. And hopefully, if the feasibility study is successful, this will then move on into a further phase of funding of actually building a carbon capture plant, which would have a capacity of 800,000 tons per year. Other parts of the roadmap were about fuel and alternative cements. So I just want to say a little bit about fuels as well. Already now in the UK, in the manufacture of Portland cement, we use 43% of refuse-derived fuel. Now that in itself does not lower the CO2, but it is a very efficient use of refuse, and it avoids refuse going into landfill. On average, we also use 17% of biomass fuels to heat our kilns, and that is truly carbon neutral fuel. Furthermore, Hansen, but also Tarmac, are involved in another government-funded project, a fuel switching project. This is about trying to fire one of our kilns with a zero carbon fuel mix. That fuel mix would contain about 70% biomass, 20% hydrogen, and 10% plasma. We are preparing currently for this trial, which is due to take place this year in July at our cement plant in Ribblesdale. Moving on from fuels, talking more about supplementary cementitious materials, which are heavily used together with Portland cement in concretes and can reduce again the CO2, embodied CO2 in concrete. The most commonly ones used in the UK are fly ash and GGBS, granulated blast furnace slag. But these also come with certain issues. Looking first at fly ash, which is a byproduct of electricity generation from coal. We have here on this graph on the y-axis the years 2012 at the top and 2020 at the bottom, and on the x-axis the numbers of days of the year from January all the way through to December. If we look at 2012, there were several days in spring and in winter where more than 50% of the electricity in the UK was still produced from coal, and accordingly fresh fly ash, which is shown here on the left, a lovely picture, SEM picture of fly ash. But moving into 2020, you might all remember the warm spring we had during our first lockdown last year, and there were several days where not a single coal-fired power station was operated in the UK. So you can see that there will be a shortage of certain UK-based fly ash very soon, or it's already here now. With regards to GGBS, GGBS is a byproduct of the iron-making process. You see here on the right-hand side a photo where the slag from a blast furnace is quenched by water. The quenching is required so that we get from the slag later the right properties for ground granulated blast furnace slag. If you look here, however, on this chart is the production of iron in the UK from 2009 to 2018. It was low after the 2008 economic crisis. It picked up again during 2014, but ever since has been on a decline. I don't have figures for 2019 and 2020, but I believe they are no better. So again, already now we don't actually produce enough fresh slag in the UK anymore for the demand for GGBS in the UK, and some of the GGBS is produced from imported slags, granulates. This leads me now on to the next section, which is about new cements, which will come into play very soon. In order to explain the new cements, I first have to explain how cements themselves actually work, how the nomenclature work. Cements are defined in the European standard EN 197-1, and this standard still applies to the UK as well, despite Brexit. In this standard, there are a total of 27 cements in 5 groupings, and they include additions like fly ash, silica fumes, GGBS, and pozzolanas. To keep it simple, I've just chosen some examples here to explain the system of cement nomenclature. So I've chosen 3 groups here, 3 common groups, CEM1, CEM2, and CEM3. And CEM1 is what probably most of you are familiar with, Portland cement, which consists of 95 clinker as a minimum and a maximum of 5% of other constituents. The CEM2s are currently divided into 2 groups, CEM2As and CEM2Bs. The CEM2A cements allow up to 20% of other additions. So for example, a CEM2ALL can have, in addition to the clinker, up to 20% limestone. And a CEM2AM can have a combination of other additions up to 20%. The CEM2B group is built up in exactly the same way. The difference is that higher replacements are allowed. Up to 35% of the clinker can be replaced by additions. The last group, CEM3, are the slag cements, where in the group A, up to 65% can be ground granulated blast furnace slag, and in the group B, even up to 80% can be GGBS. This is how the European standard works at the moment. What is the role of these in addition to Portland cement? Initially, they were introduced for economic reasons because fly ash and GGBS were cheaper than Portland cement. But many on the call of this call will also know that they are also needed for technical reasons. For example, silica fumes, fume improves the pumpability of concrete, and of course for durability, like resistance to carbonation or chloride ingress, is much improved by the use of GGBS and fly ash. And now increasingly, there is a demand for these additions because they have a much lower embodied carbon than Portland cement. I will now introduce the new so-called ternary cements. Ternary, the word says already, basically 3 components to the cement. What is the gap in the current standard for cement, EN 197-1, and the British standard for ready-mix concrete, BS 8500. I have explained that GGBS additions are required for durability, and we also want them these days for sustainability reasons. Typical additions of GGBS in the UK can already range from 30 through 50 to 70%. But the problem now comes that if you want to combine these additions with a limestone cement, a CEM2ALL, which can contain up to 20% limestone and therefore has a lower embodied carbon than CEM1, you are limited how much additions you can use. So BS 8500 for ready-mix concrete, the only option you really have is the CEM2BM option. As I explained before, a CEM2BM allows a maximum of 35% of additions. Now, if a limestone cement, which is lower in embodied carbon than a CEM1, already contains, for example, 10% of limestone, then only 25% of GGBS can be added. And 25% of GGBS is not enough to meet most exposure classes requirements in BS 8500. And of course, it also reduces environmental benefits because it's actually less GGBS than we would currently use in, for example, the slag cements. This is where the new cements come into play. A new standard is almost being published at European level as I speak. We expect it to be published this month, and the UK version, which will basically be exactly the same, should follow very soon after that. This will be part 5 of EN 197. And the additions, the new additions to this standard are summarized in the following. One of it will be in the existing SEM2 group, a new subgroup will be created, the subgroup CM. And the subgroup CM allows a replacement of other constituents up to 50%. You remember that with BM only 35% were allowed. So here we can use, say, 10% limestone and then 40% of GGBS. And there will also be a new group of cements, the SEM6 group, and it will have 4 different subgroups, including slag limestone and fly ash limestone cements. I've just given here one example. So in the SEM6 group, the minimum clinker content is down to 35%, and you can use in combination up to 60% GGBS or 20% limestone to replace clinker. The cement standard, as I said, is out due this month, but then these new cements also need to find their way into BS 8500, the UK standard for ready-mix concrete. That standard is currently being revised, and a proposal has been made to incorporate those new cements into the standard. We expect that the new revision will be issued in 2022. But there is quite a lot of work involved in order to incorporate new cements into BS 8500. So currently, these new ternary cements, which will be in part 5 of the cement standard, are not yet recognized in BS 8500. There is usually a significant validation program is required to gain the acceptance by the committee, which agrees to the changes to a standard. The Mineral Products Association led already 2 years ago started a program which was funded by the Carbon Trust and involved a number of cement and SCM manufacturers in the UK to produce data to demonstrate the performance of the new ternary cements, which we expected to come our way. This program consisted of a range of concretes being made with SEM2 BM and CM, and also the new SEM6 cements. The concretes were made to the DC2 and DC4 class, with the increasing cement content here and the associated reduced water to cement ratio for the DC4 class. And an extensive test program was carried out by the Building Research Establishment, which looked at the durability requirements for corrosion induced by carbonation and by chlorides from seawater and other than seawater. Also the attack from freeze thaw and aggressive chemical environments, as well as from seawater, and the internal degradation, the alkali silica reaction. The new cements, the concretes with the new cements were compared with concrete made with controlled cements. On this slide, I just give you one example out of many, many tests which have been carried out of this program. So here, concrete cubes were made and exposed to aggressive sulfate conditions. You see here in the middle photographs of concrete cubes which have been exposed, virtually no wearing, some wearing, and then heavily worn cubes. On the left-hand side, you see results from the new fly ash ternary cements. On the y-axis is the wear rating, and on the x-axis is the exposure time. Up to 18 months, the concrete cubes were exposed. The cements were made with 10 to 15% limestone and 10 to 40% fly ash, the remainder being a Portland cement, SEM1. And the dark lines are for the new cements, and the blue line in particular is a controlled cement, a fly ash controlled cement. And as you can see, in general, the dark lines show very similar performance to the controlled cements, with one exception here. The exception is a BM cement, which actually shows that we do need the CM cement to allow for higher fly ash additions to still get the properties with a limestone cement, the durability requirements. On the right-hand side, the graph is replicated exactly the same way, this time for GGBS-based ternary cements, again made with 10 to 15% limestone, and with GGBS additions up to 55%. And again, very similar performance to the controlled cement, which is a SEM 3A in this particular case with 50% GGBS. And again, it is the BM with a low addition of GGBS, which does not perform and which will not find its way into BS 8500. Based on the results from this extensive 2-year test program, the following proposals are being made for amendments to BS 8500. Basically, for the corrosion-related exposure classes, it is proposed there currently SEM 2BVs and SEM 3As are accepted, that in future as the SEM 2C and SEM 26 should be accepted as well. And for the free saw class, that the new cements should be accepted, and the same for designated and designated cement-bound concrete. This is a simplified version of what is being proposed just for the sake of this presentation, so I don't spend too much time on this. Associated with the introduction of the cement, what are the developments we expect for the cement industry? We expect that the SEM 2 ALL, i.e. limestone cement, which has a lower embodied carbon than a SEM 1, will eventually become the norm in the UK. So that SEM 1 will be gradually phased out as the market transfers to lower carbon options. The performance of a SEM 2 ALL can be closely matched with a SEM 1, so that the transition for the concrete manufacturer should be smooth. What have Hansen done in order to prepare for this situation? We have developed a SEM 2 ALL, a limestone cement, for bulk sales. It contains limestone levels around 10 to 12% at the moment, and I think the key is that it is the same strength class as our SEM 1, our current Portland cement. It's a 52.5 N cement. We started this development at Ribblesdale, from where this cement is now commercially available already now, and our Ketton and Padeswood cement plants will follow very soon, still this year, with the same product offering. And you will probably see it branded as a region SEM 2 ALL. My colleagues in Hansen Concrete have used some of this SEM 2 ALL to make mixes and to compare them with mixes made with SEM 1. They have added 250 kilograms of powder in one mix and also 350 kilograms. The blue line is a concrete made with SEM 1, and the orange line the concrete made with SEM 2. As you can see in those two graphs, in one the orange line is slightly higher and the other one is slightly lower, but basically we get the same performance in the concretes from SEM 1 and SEM 2. They have also made what are basically the future SEM 6s. They have blended the cement with 50% GGBS. And again, as you can see, there is virtually no difference between the two. And in fact, the SEM 2 at the early ages here has a slightly better strength performance than the SEM 1. This is a well-known effect of additional nucleation sites we get from the fine limestone in the cement. So why would you wait until BS 8500 has been updated if you can already now take some advantage of the lower carbon SEM 2 ALL compared to a SEM 1? Already now in BS 8500, if you look in part 2 in table 1, limestone cements can already be used to some extent now. So there is provision for SEM 2 ALL, for SEM 2 AM and SEM 2 BMs with slag and limestone, and also with fly ash and limestone. And they can be used in all XC, XS and XD, i.e. the corrosion resistant classes, as well as the free saw classes, and in chemical conditions up to DC2, but not DC3 or DC4. That's where we need to wait for the new cements to come in. And of course, you can also make already now proprietary concretes with a SEM 2 ALL. And of course, there are many other applications in the construction industry, not only in ready mix of cement, and the European and therefore also British standard for mortar does already now allow for a SEM 2 ALL, and the standards for screed, concrete blocks and precast paving blocks are performance-based standards. They don't actually specify which cement can or can't be used, and we are confident that the CEM2 ALL can be used in these applications. And similarly, for example, in ground engineering such as soil stabilization, again, CEM2 ALL seems a suitable application. Looking further ahead, I have mentioned before that we anticipate there will be a shortage of GGBS and fly ash at some point. Therefore, I do believe that we will hear a lot more about other cementitious replacements in future. And in particular, natural pozzolana, denominated with a P in the cement standard, and calcined clay with a Q. These are additions, main constituents of cements, which are already recognized in EN 197-1 now. P and Q also offer carbon savings, just as GGBS and fly ash do compared to CEM1, and they have also the benefit that they also are recognized for durability improvements. Some more work is due to be done to get the recognition of natural pozzolana and calcined clay again in BS 8500, although they're already recognized in there, but probably a higher acceptance in the UK market. And again, Hansen Cement are involved in those developments. So coming to the last part of my presentation, in summary, I hope that I've been able to demonstrate that there are many approaches underway to address the CO2 challenge associated with cement and concrete, such in particular as carbon capture and storage, using different fuels, using supplementary cementitious materials. The new standard for ternary cements, which allows the use of limestone cement together with, for example, GGBS or fly ash, will be EN 197 Part 5, and we expect it to be published at European level this month and very shortly afterwards in the UK. BS 8500 is also under review at the moment, and the new edition, which we hope will be out at the latest by the end of 2022, will incorporate the new CEM2 CMs and CEM2 6 cements. In order to prepare for this, Hansen have developed a CEM2 AL bulk cement offering, which is already available now and which can be used now. And looking much more long-term, I do believe that we will see a lot more, many more different SCMs entering the market eventually, such as natural pozzolanas and calcined clays, because of the durability and carbon benefits they give and the potential shortage of GGBS and fly ash. Thank you very much for your attention. I see there's a little bit of time for questions. I just need to see whether my colleague who has been looking at the questions has sent some of these through to me. One moment, please. So one of the questions I can see is, so realistically, how low carbon can we make cement? Do we need a reduced carbon price to reduce concrete use in design? Do we need a carbon price to reduce concrete use in design? There is already now a price associated with carbon through the carbon emission trading schemes. Environmental product declarations are available already now, for example, for CEM1 and also for GGBS, which will show you that GGBS in itself has a much lower carbon content, embodied carbon, than CEM1. For the new cements, because we actually haven't made them yet, we don't have EPDs available. It's a bit of chicken egg situation. You need to actually produce the cements to have good data, and only good data will deliver credible environmental product declarations. We will publish product declarations for our CEM2 ALL, and later this year, once we have produced it at all our sites. And I do expect that the carbon of a CEM2 ALL will be, the content will be between 50 and 70% kilograms per ton of cement lower than for a CEM1. Another question, I believe, is, can captured carbon be locked up in new concrete? Yes, indeed it can. And quite a lot of developments are ongoing because concrete can be cured, i.e. strengthened with CO2. So CO2 curing is a known and available technology. It does require further development, primarily for the practicalities, because ideally, for example, this is a process which is very suited for precast elements or also concrete blocks, for example. But ideally, you then want the factory where the elements are being made being very close to where the carbon is being captured. So, for example, on cement works. Another way is CO2 can be transported, it can be captured from the cement works, but it then needs to be very pure so that it can be compressed and liquefied for transport to where it is actually needed. So yes, it can be used, but there are logistic aspects which need to be considered at the same time. Another question was about, have we done a carbon comparison for the new ternary cements? As I said, we haven't got verified figures yet, but we have figures separately for GGBS, which is at around 80 kilograms of CO2 per ton, compared to a much higher, around 800 kilograms of CO2 for a CEM1. So from this, you can deduct the the benefits of blending with GGBS. And as I mentioned before, we will also get product adaptations for our CEM2, which will show again a reduction compared to CEM1 with regards to embodied carbon. Thank you very much. I think these were all questions which have come through to me. I would therefore like you to thank you for your attention. Some of my colleagues, Robert and Townsend and Michael Wildmore, I think are still available throughout the day in case you have any further questions. Thank you very much and goodbye.